Hello and welcome back to another one of my videos on how to use the CRP-5. If you're watching this video, you're in one of two categories. You either want to know how to calculate true altitude on a CRP-5, or you've stumbled in drunk on a Saturday night and YouTube has for some bizarre reason recommended my channel to you, in which case I think you should definitely subscribe and watch this video because it's going to be fascinating. So, today we're going to be looking at how to calculate true altitude on a CRP-5, and as usual I'm going to give you a bit of theory as to what true altitude is before we discuss the ins and outs of how to calculate it. So first of all, what is true altitude? Well, you need to understand that the altimeter in your aeroplane is not always accurate. In actual fact, it's almost never accurate, because the altimeter in your aircraft is only calibrated to ISA conditions. And I'm sure you're aware that when you're flying on an average day, the weather is very rarely equal to a standard atmosphere. It's usually always above ISA or below ISA to some degree, either the pressure or the temperature. So in other words, any meteorological condition that deviates from ISA, which is usually always, will result in an error. And that error is proportional to the ISA deviation, and therefore the height of the aircraft above whatever pressure datum you're using will be affected, whether you're higher than you think you are or lower than you think you are. Now there's something we need to take into consideration called the temperature error correction. Sometimes you'll see it written as TEC, and this is the accepted calculation from ICAO and the CAA, and it says that the error induced will be equal to a 4% height increase for every 10 degrees Celsius below standard temperature as measured at the altimeter setting source. In other words, if the temperature is 10 degrees below ISA, then the error on your altimeter will be equal to a 4% height increase. In other words, you will falsely be reading that you are 4% higher than you think you are if the temperature is 10 degrees below ISA. Okay? Likewise, if the temperature is 10 degrees above ISA, then your altitude, your indicated altitude, will be 4% lower than you think you are. Now that's obviously very beneficial, because if the temperature is higher than you think you are, but your indicated altitude is lower than you think you are, that means that your true altitude will always be higher than indicated, which is a good safety margin for terrain clearance. So just to clear up, if the temperature is warmer than the standard, then we are higher than we think, which is good. However, if the temperature is colder than the standard atmosphere, then we are lower than we think, and this is a big problem for terrain clearance. So if there's an obstacle, for example, that is say 3,500 feet tall, and I'm indicating I'm at 3,700 feet, although I'd be fairly foolish to only give myself a 200-foot margin, in theory, in an ISA atmosphere, I would be able to clear the obstacle by 200 feet. But if the temperature is lower than ISA, then I might actually find myself being potentially 1, 2, 3 or 400 feet lower than the obstacle. So here's a diagram just showing what we're talking about. And you can see here that as the temperature drops, you can see here at the bottom, we've got 30 degrees Celsius, 15 degrees Celsius, and 0 degrees Celsius. And we've got our little aeroplane here, and you can see that on every one of these instances this aircraft is indicating 5,000 feet. So every one of these pilots thinks they're at the same altitude, but you can clearly see that because they're all flying in different temperatures and different atmospheres that deviate from ISA, with the exception of this middle one who is flying in an ISA atmosphere. These other two aircraft are going to be potentially significantly higher or lower than they are indicating, because of the fact that as the temperature cools down, then the pressure levels get closer and closer together because the air contracts. And likewise, as the temperature increases, then as we said in the video on density altitude, then the air expands because the air is warmer, and therefore you end up flying higher than you think you are because the spacing between the pressure levels increases. Now, having a temperature which is higher than ISA is a good thing. Having a temperature which is lower than ISA is clearly not very good. So how do we calculate this? Well, we need to use something called the temperature error correction equation, and this is it. It looks a bit daunting, but it really isn't. It states that the true altitude is equal to the indicated altitude on QNH plus 4 times the altitude in thousands of feet multiplied by the ISA deviation. Now 4 comes from the fact that there's the 4% rule that we discussed on the last slide. Now what is this thing here? Because the ISA deviation is fairly obvious. This thing here, the altitude in thousands, is simply the vertical displacement from the bottom of the aircraft to the nearest surface below the aircraft. In other words, the height of the column of air below the aircraft in which the temperature error can exist. So if you can imagine a column of air from the aircraft to the nearest surface, solid surface below the aircraft, be that ground or the sea, that's the column of air in which a temperature error can exist. Okay? So, let's look at 3 different examples, an easy, medium and a hard. So, an aircraft is flying at an indicated altitude of 16,000 feet. The outside air temperature is minus 30 degrees Celsius. What is the approximate true altitude of the aircraft? Now, I'm going to point something out to you straight away, and that is, if you see the word approximate in an exam, specifically for the CAA ATPLs, I'm not sure if it's the same for all of Europe, but if you see the word approximate, it's usually because the examiner wants you to use some kind of back-of-the-envelope calculation, a general rule of thumb, or a CRP-5, because none of those 3 things are accurate. Okay, if you see the word an approximate calculation, it usually means the calculation has been done in a roundabout fashion without being too accurate. Okay, and you'll see why that's somewhat important in a moment. So how do we do this? Well, first of all, we need to start drawing out our pressure levels. Number 1, notice that we're talking about altitudes, so we care about QNH. So the QNH has been put in, and QNH, as you know, is the pressure level found at sea level. Now the aeroplane is flying at an indicated altitude of 16,000 feet. So I'm going to draw my aeroplane in here, 16,000 feet above the only known surface that I've got. And although it doesn't tell me what the QNH is, it doesn't matter because it tells me that I've got an altitude and it tells me that I'm 16,000 feet. Altitude means sea level, 16,000 feet above sea level. That's what it means. Now the temperature is minus 30. How is that any use to us? Well, it's useful because at at 16,000 feet, I know that the temperature should be minus 17 degrees Celsius, and that's based upon the temperature lapse rate of 2 degrees per 1,000 feet. However, the temperature is minus 30 degrees, which means that the temperature is 13 degrees below ISA. So we have an ISA deviation of negative 13 degrees Celsius. The true altitude, therefore, based upon the equation that we discussed a moment ago, is the indicated altitude on QNH, which in this case, if I were to set QNH, I would indicate that I'm 16,000 feet above sea level, plus the temperature error correction, and that's 4 times the altitude in thousands, or the height of the air column in which the temperature error can exist, which in this case, the amount of air between the bottom of the aeroplane and the nearest surface is 16,000 feet. In thousands of feet is 16, multiplied by the ISA deviation. And if you carry out that calculation, you'll get 16,000 minus 832 feet. And again, remember, the plus and minus will give this whole bracket a negative value, so plus minus is a minus. So 16,000 minus 832 should give you an answer, according to a calculator, of 15,168 feet. The actual answer from the CAA is 15,200, and this is more than close enough. The spread of answers in these exams for these type of questions specifically asks you to calculate an approximate altitude is usually plus or minus 1,000 feet at least. So to get to within, about 32 feet is very, very good. So that's how you do the calculation according to maths. Let's now do that on the CRP-5 and see if we get a similar answer. So I'm going to find my CRP-5 here. And for this we're going to be using, as I said previously in the density altitude video, we're going to be using the altitude window for true altitudes. Remember, airspeed window for density altitudes, altitude window for true altitude calculations. So what we're going to do is simply set up our temperature and pressure altitude, which in this case, all we've got is 16,000 feet, and the temperature is minus 30 degrees. So here's minus 30 degrees, and we're going to set up 16,000 feet. which is 16,000 gets minus 30. Okay, and then what we do is we look on the inner scale of the CRP-5 for our indicated altitude. Technically that's not true. What we're looking for on the inner scale is the height of the column of air in which the temperature error can exist. Now in this instance that is equal to the indicated altitude, but it won't always be, as you'll see in a later example. So we want to put the height of the column of air on the inner scale, because that's the only height, the amount of air in which that temperature error can exist, and then we're going to look for the the true altitude on the outer scale. So let's look for 16,000 feet on the outer scale, or should I say inner scale. 16,000 feet, and look at that, 16,000 feet on the inner scale, and we get almost exactly 15,200 feet on the outer scale. So the inner scale here is telling me the height of the column of air, and the outer scale is giving me my true altitude. Okay, so let's now look at a slightly more tricky example. So here we have an aircraft which is flying now at flight level 160. The outside air temperature is minus 27 degrees Celsius. The QNH is 1003. What is the approximate true altitude of the aircraft? Now, first thing we need to note with this question is that we are now given a flight level. We're given a flight level and a QNH, so we need to take into account both the pressure at sea level and also the pressure level at 1013, where the flight level is based on. Now remember, the flight level is effectively a pressure altitude. That's why we have to base it upon the standard pressure setting of 1013. So there's my 1013 line, and my QNH is 1003, which is a lower number than 1013, which means on the diagram it comes higher in the atmosphere. Okay, it's a lower pressure, so it must be higher in the atmosphere. And I can draw in my aircraft, which is at flight level 160. Now note that this is 16,000 feet, but it's 16,000 feet relative to 1013, not relative to 1003, okay, because that would be an altitude of 16,000 feet, not a flight level. So I can draw my 16,000 feet line in there relative to 1013, and I can also draw in the height of the difference between 1013 and 1003, which is 10 hectopascals, assuming 30 feet per hectopascal. Okay, I know for some subjects like meteorology it's 27 feet, but GenNav particularly is 30 feet. So 10 times 30 is 300, so I know that the height difference between these two pressure levels is 300 feet. That tells me that my indicated altitude on QNH, if I were at this position here at 16,000 feet relative to 1013, if I set QNH of 1003, my altimeter would indicate that I'm 15,700 feet above sea level. But my true altitude would be, well, let's find out. Now the icy temperature at 16,000 feet, as in the previous example, should be minus 17 degrees Celsius. However, we know that we're at minus 27, so we're 10 degrees colder than ISA. So the ISA deviation is negative 10. Putting this into the equation gives us indicated altitude, which is 15,700. Remember, that's indicated altitude on QNH, plus the temperature error correction, which is 4 times the height of the column of air below the aircraft, which again is 15,700 feet, in thousands of feet is 15.7, multiplied by the ISA deviation, which we said was minus 10. And that will give you 15,700 minus 628 feet, which gives you 15,072 feet. The CA answer is 15,090 feet, so this is incredibly accurate. Okay, and again, note that the temperature is below ISA, as we can see from here, so we know the answer is going to be less than our indicated altitude. So we're indicating 15,700 feet, but we're actually only at pretty much 15,000 feet. So in this case, we're about 600 feet lower than we think we are, which is quite a big difference. So let's see how we do this one on the CRP-5. So there we go. So let's have a look. So in this window now, we now need to again put in our pressure altitude or equivalent, which in this case will be 16,000 feet, because remember this is pressure altitude, which effectively is what a flight level is. It's relative to the same pressure datum. And the outside air temperature is minus 27. So 16,000 feet, which is there, and I want to put this to minus 27, which is about, there's minus 25, 27, that's about 16,000 feet at minus 27 degrees Celsius. And again, on the inside scale, what I want to do is look for my column of air height, which is 15,700 feet. And you can see from here, if we set up 15,002, 4, 6, 7, I get these indications are about 200 feet apart. So again, I'm getting about just north of 15,100 feet, depending on how accurate this scale is. On an actual CRP-5, you'll get pretty much the same value. So as you can see, the answer of 15,090 feet is incredibly accurate using the CRP-5. And again, remember, the spread of answers will be usually plus or minus 1,000 feet at least. So if you're 100 or so feet out, it's really not a problem. Next, a slightly trickier example still. Let's look at this one. We have an aircraft which is flying at a flight level 100. The outside air temperature is minus 15. Correction, it is ISA minus 15. The QNH given by a station at an elevation of 3,000 feet is 1035. What is the approximate true altitude of the aircraft? A couple of things to note with this question. Number one, as always, is asking for an approximate true altitude. That means that the examiner has calculated the answer using the CRP-5. Secondly, note we're now given a station at 3,000 feet. Although the examiner hasn't explicitly told you, what this question is getting at is that the examiner wants you to be able to calculate the true altitude above this station. It doesn't tell you that, but that's what it means. If you ever see one of these questions and it gives you the QNH of a local airfield or a local meteorological station at a given elevation, sometimes the elevations are above or below sea level. It wants you to calculate it above the station. Okay, and you have to take that into consideration, as you'll see from this example. So as always, let's start drawing in our pressure levels. Now notice the QNH here is 1035. Now that's quite a high pressure, and it's higher than the standard of 1013. So again, make sure you draw the diagram correctly. Note that the QNH is a higher value than the standard pressure setting, so we draw it below the 1013 pressure datum in the atmosphere. We're going to put our aeroplane up here, which is at flight level 100, which is 10,000 feet above 1013. Okay? Then we can work out the height of the difference between these two pressure settings, which is 1035 minus 1013 equals 22 hectopascals, multiplied by 30 feet per hectopascal, which gives us a difference of 660 feet. That tells us that our indicated altitude on QNH, were we to set this aircraft's altimeter to QNH at this point in the flight above sea level, it would indicate 10,660 feet. The question is, are we actually 10,660 feet above sea level? Well, we can see that we're 15 degrees below ISA, so we know that we're not. We're going to be less than this value. Now note, we have some terrain in here. This is supposed to be grass, by the way. I spared no expense whatsoever in figuring out how to do that. So this is the terrain, and this is our 3,000 feet, because this is the station that exists at 3,000 feet above sea level. Because we've got an elevation, remember elevation is the height of an obstacle on the ground relative to mean sea level. So this is our 3,000 feet. As a result, we can work out the 10,660, which is our indicated altitude above sea level, minus the 3,000 feet, tells us that we are 7,660 feet above the station, or above the nearest surface. So this is the important number that we need to calculate, because this is telling us what the column of air is directly below the aircraft. This is telling us the height of the air column in which the temperature error can exist. The height of the air column is not 10,000 feet, and the height of the air column is not 10,660 feet, because we're assuming in this type of question that we are many, many hundreds of miles inland, and this is the nearest surface. Okay? So in terms of the calculation, we have an ISA deviation of minus 15, which we're told in the question. And again, be careful to read this carefully. Make sure you read it as ISA minus 15, not the temperature is minus 15 degrees, because that will give you a very different answer. So the true altitude is therefore the indicated altitude on QNH, which we said was 10,660 feet, plus the temperature error correction, which is 4 times the height of the air column in thousands of feet, which is the 7,660, multiplied by the ISO deviation of minus 15 degrees. Therefore we get 10,660 minus 460 feet gives us a true altitude of 10,200 feet. So you can see that our indicated altitude is telling us we're at 10,660, when in actual fact we're over 400 feet lower than that. So from a terrain clearance point of view, very, very serious. And let's look how to do this one on the CRP-5 as well, just to prove the point. And the CAA answer for this exam was exactly 10,200 feet. So we got it spot on. So what we need to do with this one, now just to warn you, I've done this a couple of times on this CRP-5 and on my actual CRP-5, and I don't quite get exactly the same answer, but again the spread of answers is usually plus or minus 1,000, sometimes 1,500 to 2,000 feet. So being a couple of hundred feet out on a CRP-5 is not important. Why? Because as I said, the examiner asks you to calculate the approximate true altitude, not the actual true altitude. So what we're going to do is we're going to line up our flight level 100, which is our pressure altitude, with the temperature of minus 15. So you have to work out the ISO deviation here. We're told that the ISO deviation was minus 15, so at 10,000 feet the temperature should be minus 5. If we're 15 degrees below that, then we should be at minus 20. So I'm going to set up 10,000 feet, which if you look at this graduation here, we've got 5, 6, 7, 8, 9, 10, and we're going to line that up with minus 20 degrees. And then on the inner scale, we're going to look for our indicated altitude on QNH, which we said was, what did we say it was? It was, I believe, 10,660. That's going to be up here actually. So 10,660 is 10,000, 1, 2, 3, 4, 5, 6. 10,660 is about there. And you can see that I'm getting on here a true altitude of just over 10,000 feet, about 10,050. Again, on this one it's about 150 feet out, but if you were to look at the answers available, there's no chance that you would definitely get it correct. Okay, so that's how you calculate true altitude, both using the equation and on the CRP-5. Important things to consider are, don't forget that the inner scale of the CRP-5, you want to put your indicated altitude on QNH, okay? And don't forget, in the equation you need to be very careful to ensure that if you're using this method, this number here, the height in thousands, is the physical height of the object above the nearest surface. It's basic altimetry. If you want me to be really honest, I rarely use the CRP-5 to do true altitude calculations. If you've got to use the if you've got to use the equation to figure out the ISO deviation sometimes and what the column of air is to work out what your potential indicated altitude is to use a CRP-5, I just continue using the equation to come up with an answer every time. Any questions, comments, don't be afraid to ask, and I'll be back fairly shortly with another video on how to use the CRP-5.